Hi, I'm Linus. I'm going to talk about how we synthesize constrained and robust policies in uncertain environments. We'll do this by combining SMT solvers and probabilistic model checkers. I'll explain our problem statement using this example. This robot is in a grid where whenever it tries to move in a direction, it will move forward with probability 0.9 and slip to the left instead with probability 0.1. Our goal is to find a policy for this robot such that it collects all four rocks with probability bigger or equal than 0.9. Specifically, we want that policy to work wherever the rocks are and to be described by a simple set of rules. By simple set of rules, I mean something like a small decision tree instead of a big lookup table. The fact that we want the policy to work in all environments is a property that we call robust. And the fact that we want the policy to fit in a certain description is a property that we call constrained. Even though this problem looks quite simple, some previous work could not find any robust policy for this environment. But we can solve this problem, and in the end we will see the solution. The challenge of this sort of problem is that we have a combinatorial search space of policies and environments, and we also have uncertainty such as the slipping probability for the robot. There are existing approaches for these sort of problems. One thing you can do is encode it into a mixed integer linear program, MILP, or another monolithic encoding such as an SMT query with linear real arithmetic. This works, but it's known to be much slower at evaluating the policies of the Markov decision processes than dedicated methods such as value iteration, and we will see that in the experiments. Another thing that you can use is an abstraction refinement algorithm such as branch and bound, but this is limited to problems with particular search spaces, so you can't reason about arbitrary constraints. Our approach, called SMPMC, is to combine SMT solving and probabilistic model checking, where the search space and constraints are handled by the SMT solver, whereas the underlying Markov decision processes are solved by a probabilistic model checker, for example using value iteration. Before I show you how the integration between the SMT solver and the probabilistic model checker works, I'll first show you the input formula that we give to the SMT solver. It looks as follows. Does there exist a policy described by these variables x, such that for all environments described by the variables y, if the constraint holds, the constraint is written as tau, the probability to reach the goal is bigger or equal than some threshold nu, and this is written down as this viable statement. So this last statement viable will be evaluated by the probabilistic model checker. This is called a custom theory in SMT solving. And now I'll show you how we evaluate that viable using the probabilistic model checker. Now here's how we evaluate viable. The SMT solver will pick a partial assignment of the variables in viable, for example setting x1 to 1 and x2 to 2. And we have not picked a value for x3 yet, so this is left open. The probabilistic model checker checks whether this partial assignment could be completed to a full model by evaluating a Markov decision process. And if that's not possible, then it will push back a theory conflict. So here, if it pushes back this theory conflict, it can never be the case that x1 is 1 and x2 is 2. This is similar to two other approaches, and I'll tell you why it's different to them. In a guess and check algorithm, the SMT solver would propose full assignments, which is a full guess, to the probabilistic model checker, which will then check it. But here, we will already start checking once the SMT solver makes its first decision and assigns the first variable. Thus, we can prune branches much earlier. Later, we'll see that we are as good as a guess and check algorithm on constrained search spaces, but we are much better on other problems. In an abstraction refinement algorithm, such as branch and bound, there's a bespoke refinement algorithm that's here in the place of the SMT solver that explores the search space, and it can only handle search spaces of a certain shape, whereas an SMT solver can solve whatever search space we want. Later, we'll see that we are as good as a state-of-the-art abstraction refinement algorithm, even on simple search spaces. Now that we've described our method, let's get to the experiments. We ran experiments on a set of 372 benchmarks, which is quite diverse. For example, we have benchmarks that do verification of sets of Markov chains. We have finite state controller synthesis on partially observable Markov decision processes, and we have policy synthesis and multi-environment Markov decision processes. So our comparisons are as follows. There's Paint, which is a state-of-the-art policy synthesis tool that implements both guess and check and abstraction refinement algorithms, and a monolithic SMT query that uses linear real arithmetic. So the first question is whether on problems that are already solved by other tools, is SMPMC competitive with the best tool on each problem? And the second question is whether we can solve this new problem statement that none of these tools can solve, which is constrained and robust policy synthesis. We'll start with a comparison against the baselines and synthesis problems where we have a single environment. In these plots, the farther the right a curve goes, the more problems the method has solved in the 30-minute timeout, and the lower a curve goes, the faster the tool has solved those problems. So a lower curve is better. In the left plot, we have synthesis without any constraints. Here, SMPMC is competitive with abstraction refinement. We solve almost the same number of problems, whereas the other methods lag significantly behind, including Paint-Seeges, which is the guess and check algorithm implemented in Paint. On the right, we have synthesis with constraints, so constrained synthesis. Here, abstraction refinement does not work because we have constraints on a search space and cannot handle that. But SMPMC is competitive with Paint-Seeges, which is the guess and check algorithm. So it turns out that previously you would have to employ different tools to be good at these problem statements, whereas SMPMC is good at both without any tweaking. In the paper, you will see that this is also true for robust, unconstrained synthesis. In both plots, you can also see the line labeled SMT-LRA, so this is the monolithic SMT query that uses linear real arithmetic instead of a probabilistic model checker to evaluate the MDP policies. And as this method lags significantly behind SMPMC, we can confirm that using a probabilistic model checker instead of linear real arithmetic to evaluate the Markov decision process policies helps a lot. So for constrained and robust policy synthesis, we've already mentioned that SMPMC is the first effective tool to handle this problem. So now we'll go back to the problem statement from the beginning and show how to solve it. So for this example, SMPMC finds this 5-node decision tree that solves the problem. That means it makes the robot pick up all rocks with probability 1 eventually. And how it works is that it picks up all rocks in a spiral. If x is bigger or equal than 6, we go up, and there we could slip left. If that's not the case, but y is bigger or equal to 2, we go left, and there we could slip down, and then otherwise we go down, and there we could slip right. The policy of the robot, combined with these slipping dynamics, creates a Markov chain where the spiral effect ensures that we will eventually visit every cell, and that means that we will pick up all rocks with probability 1 wherever the rocks are. In conclusion, we presented SMPMC, which is a novel, versatile, and efficient approach that tightly integrates SMT solvers with probabilistic model checking. We showed that it's the first effective approach that constructs robust decision tree policies. It's competitive with the state-of-the-art heuristics on problems that they can solve, but it also solves new problems. You can also find our paper and our open source code by scanning the QR codes.